this was, all those algorithms belong to the so-called supervised learning category, where you have some inputs and outputs, and you want to learn a function between those inputs and outputs. And today we will start a new topic, which is called unsupervised learning, where you just have a bunch of inputs and you want to learn the structure in your input vectors. And clustering is one of the most popular unsupervised learning topic, I would say. So the contents for today is that we will briefly discuss the clustering problem, what it means to do clustering, and then we will discuss two algorithms for clustering, the k-means clusterings and the mixture of Gaussians. So there will be two algorithms for that. And then we will see that somehow they are special cases of a more general maximum likelihood estimation methods, which is called expectation maximization. So expectation maximization will be a general framework to do maximum likelihood estimation in certain models. And it turns out that k-means algorithm and mixture of Gaussian EM method for mixture of Gaussians are special cases for this. And then we will see another generalization of expectation maximization, which is called variational methods, that you can use in certain cases where you cannot use EM. Okay, so we will see the details of that. Bottom line is, these are some maximum likelihood estimation methods that you can use in certain cases, and we will discuss what are those cases when you can use these approaches. Okay, but before that, let's start discussing clustering problems. So what is clustering? Clustering is a process of grouping set of objects into classes of similar objects. So we somehow want to group objects. The difficulty is that even in the training set, we don't have class labels. If we have class labels, we call it classification. If you don't have class labels, still you want to do grouping, then we call this problem clustering. And what we want is that inside those classes or clusters, we want high intra-class similarity. So those objects that belong to the same cluster, they should be similar to each other. And those objects that are in different clusters, they should have low similarity. Okay, so one problem is that, oh, by the way, the slides are on the website, so you can just download them, print out, and make your notes there too. So the clustering is subjective. So for example, if I have these Simpsons characters, and I ask them to cluster them, then you can do that in many different ways. So for example, one possible clustering is that the Simpsons family could go to in one cluster, school employees to go to another cluster, or females and males could go to other clusters. So if I just say that, hey, here is the data set, cluster that, it's not a well-defined problem, because the clustering defines on the similarity that you also should provide to us. Okay, the other thing is that sometimes it's, for us humans, it's difficult to define what we mean on similar, but when we see similar things, we recognize them. So anyhow, what we will do is that we assume that there's already a similarity function or a distance function. Someone gave that to you, and we will just use that in our clustering problems. Okay, so let's start discussing the k-means clustering problem first. So it's not an algorithm, so it's a problem, k-means clustering problem. Here is the problem. So given a set of observations or feature vectors, x1, x2, xn, so they are, say, all d-dimensional feature vectors, and we want to partition these n observations into k sets. Let's denote these k sets with s1, s2, sk. So they are all sets of the feature vectors, such that we want to minimize the within cluster sum of squares, where in this expression mu I is the mean of the points in the set Si. Okay, so you have a bunch of Oops, sorry. So we have a bunch of points, feature vectors. We want to group them into sets. Say this is S1, say this is S2, I don't know, S3, S4, such that each set will have a mean vector. So say this is mu1, this is mu2, this is mu3. So each set has a mean vector, mu4. And we want that the distances from each instance, each object to its cluster mean, you calculate this square distance, and we want this sum of squared to be minimum. So you want to minimize over the possible set allocations such that this cost function is minimum. Does it make sense so far? Very good. So here is my first question. How difficult is this problem? So what do you think? So the problem makes sense, right? So you have n instances, x1, x2, xn, and you want to minimize over allocations. So you want to find those sets S1, S2, S3, S4 that will minimize this cost function.
So K is fixed beforehand? So
K is fixed beforehand, right. So K is fixed, say 4 in our case. K is fixed. So my question is how difficult this problem in the number of instances n? Or, okay, so let's start with this. How would you solve this problem? So here is this cost function. You can tell me any naive algorithm that comes to your mind. Just you see this cost function. We want to minimize this cost function over S set allocations. How would you do that?
Enumerate all the possible congruences.
Exactly, very good. So you could just list all the possible allocations, set allocations, and see where it's minimum. The only problem is that there's exponentially of many of those in the number of n. So, and that would mean this problem is NP hard if you cannot do something better. The question is whether we can do something better or not. Right, so this is just the formal setting of the problem. Again, we have n instances and we want to group them to say, in this case, 3 classes, such that these are the class centers, that this sum of squared Euclidean distances, they are minimum. And one algorithm, you just do brute force. The only issue is that we have n instances, k classes. It would be exponential long list of possible allocations. If we want to count the minimum, it's NP hard problem, if we cannot do something better. So it turns out that this problem is indeed NP hard. So we just started the very basic unsupervised learning in machine learning, and it turns out that's already NP hard. So let's go home. We cannot do anything. So, but what does NP hard means? It just means that in your problem class, there are difficult instances. It doesn't mean that your life will always be that difficult, right? It's just if someone is cruel to you, it can give you a difficult instance that you cannot solve. The other thing is, so that's what NP hard means. The other thing is that quite often we don't care to find the global optimum with this solution. If we find a good enough one, then we are already happy with this. So that's what we are going to do. So we have this cost function. We have to accept there are difficult instances that we cannot solve. But we will look at two algorithms that are good heuristics in that sense that they seem to work well in practice. So one algorithm is called the k-means clustering algorithm. So that was the problem, right? It's not an algorithm. There will be an algorithm that tries to solve this problem. That's called the k-means clustering algorithm. And there will be another heuristic, which is called mixture of Gaussians, that also in practice seems to be a good heuristic to solve this clustering problem. Okay, so let's start with the k-means algorithm. I'm just curious who knows the k-means algorithm. So it's like half of the class, very good. But I hope those who don't, it's a very simple algorithm, so I'm sure you can follow me. So here is how the algorithm goes. You have n instances. So now we are in this 2D space. And you guess the cluster centers. So for example, you start with K1, K2, K3, just randomly. Okay? Right, so I don't want to confuse you always with notations, but in the previous slides, these cluster centers were mu1, mu2, mu3, but now they are K1, K2, K3. And then what you do, that you build a Voronoi diagram. If you don't know Voronoi diagram, please raise your hand now. Also, another thing, right, then I will explain. So another thing you can do, if you think it's too embarrassing to ask these questions, you can say that I think the guy next to me doesn't know this. And then just point to someone, look at his face, he doesn't know. Okay? So just my point is ask questions. If you don't know something, it might mean that probably there are other people who don't know. Yes?
Could you raise an example of the clustering is NP-hard?
Yes, clustering is NP-hard.
So could you raise an example to show that?
I can give you a paper to that where they show a difficult example. All right, so this is what we do. So we have n instances, and we guess cluster centers. So say K1, K2, K3. Obviously, if you look at these guess one, they don't look good. But this is how we start our algorithm, just some randomly selected cluster points. And then what we do is that for each cluster point, we calculate what are those instances that have minimum distance to these cluster points. So for example, this is K1. Then this point has minimum distance to K1. This point and all these points have minimum distance to K1. Right? These points here, they are the closest cluster center is K3, and these points here, the closest cluster center is K2. So for each point, say this point, you calculate what's the distance of this to K1, to K2, and K3, and you choose the minimum one, and then you will say that this point belongs to K1. And it turns out, it's easy to see that the decision boundary, which decides which points belong to which cluster center, in this case is just, so the decision boundary is just straight line segments in this case. And that's what we call Voronoi diagram in this case. But for now, what we need is just for each point, you don't even need to build these straight lines. You just have to calculate for each point the distance to these guessed cluster centers and choose the minimum. And then you will say that, hey, these points belong to this cluster. So that's the first step of the algorithm. Is that clear so far? Good. The second step, that now we have this allocation, we re-estimate our cluster centers. So now I know that I allocated these points here to K1, and let's count the center of these points. And that will be my re-estimated cluster center in this class. Okay, and I do the same here. So these points belong to K2, re-estimate the cluster center, it will be somewhere here, and this is how I update the cluster centers. All right, and then I have new estimated cluster centers, and I do this process again. So I estimate which points belong to K1, which points belong to K2, which points belong to K3, and I do this new allocation, and I re-estimate the cluster centers again. And I do this till I converge somewhere. Does it make sense, the algorithm? Okay, so this is what's called k-means clustering algorithm, and you stop when nothing changes anymore. So when in the next iteration the same points would be allocated to the same cluster center, then nothing changes anymore, and then you can just stop there. Yes?
Can you prove that that happens?
So that's a very good question, right? Exactly. So that's a good question. So why would this happen? So it might happen, right? Why doesn't it happen that I get to a loop or something?
Because in each step, your objective does not decreases, basically.
Right. So we will see a proof for that. There's an objective. Actually, this objective, and then we will see that when we run this algorithm, in each step, the objective won't decrease. It either stays the same or decrease. And because I have only finite allocations, it means that at some point the objective just will stop decreasing.
Yeah, but then you can still change it. It doesn't mean that you...
Right, so if you have randomly selected points, it will not really happen, right?
So you mean we measure one?
Yes, you will stop, yep.
Okay.
All right. So this is just formally the algorithm. You have input x1, x2, xn, and k is also an input, how many clusters you want. And then you just do this two-step iteration. First, you decide the class membership, and then you update the cluster centers. And you do this iteration. Any questions so far? So that was simple. Let's count the computational complexity of this algorithm. So for each of these n objects, I have to count what's the distance of these objects to the k cluster centers. So that's n times k computation. And once I did that, I have to allocate a cluster center to each object. That's another n operation. And I do this iteration, say, till L times, so then it would be big O L K N, capital K N. And we just touched briefly this question, whether we can prove that the k-means algorithm is going to terminate. Yep.
The complexity include the complexity of doing the deep dimensional Voronoi diaphragm?
So that's here. So I just assume that you have we have n d-dimensional instance, and so say here is an instance, and I already have a cluster center, and I assume that to calculate this distance here is just a constant computation. And that's what you need. That you just need to count for each instance. What's the each instance? What's this Euclidean distance? What's this Euclidean distance? This Euclidean distance, and this Euclidean distance. And that's why it's big O K N. So that's what we all need from Voronoi diagrams. Okay. So another important thing here, that we start from some randomly selected cluster centers that we call seed. The algorithm is very sensitive to that. So for example, here is this problem. Apparently, if I ask you to find 3 clusters here, then ideally you would say 1 cluster, 2nd cluster, 3rd cluster. But if you start from these 3 random points, then this is how the algorithm would converge. So at the end, you are here, and then everything settles, and that's where the k-means algorithm would stop.
So you find something on local minimum.
Exactly. So from a random starting points, you will converge to a local minimum point of your cost function. Yes?
You said the complexity is K and L,
Mhm.
and we know K and we know N,
Mhm.
but is there a way to estimate how many iterations we need, or at most how many iterations?
No. Especially because in the worst case, it can be exponential. So not with this algorithm. There are some improved versions where you can at least, so you can have some bounds that you will never say I found the global optimum of this algorithm after this many iterations, but you can say that, say, I'm not too far from that global optimum points. You can say this kind of guarantees. But we will not touch those algorithms.
Sorry.
Yes?
Are there any good heuristics as to initialize these?
Very good question, and there are. So if you are interested in details, look at the k-means plus algorithm. So other questions you might ask, what to do with the number of clusters? Why this algorithm it's a very strong constraint that you have to say, I want 3 clusters. And it would be nice to have an algorithm that can also estimate how many clusters I need. And there are versions for that one as well.
What do you mean by how many clusters you need?
So you look at the data, and somehow you want the algorithm to decide what's the optimum number of clusters for that.
So you also penalize going big?
Yes,
Because
exactly.
you take N,
Yep.
then you're done.
So, right, so what you do that you penalize for the complexity, and then you want to do this in a meaningful way. And so in Bayesian non-parametric methods, people do that. But we are not going to go to the details of that. My point is that there are algorithms that try to estimate the number of clusters as well. Okay, so with k-means, what you can just do, you try many different random starting points and you choose the best one. Okay, so this algorithm was a alternating optimization method. So formally what we did, that we had some randomly initialized cluster centers. So I just denote them with mu naught, which just means that at time step 0, mu1, mu2, mu-k were the cluster centers. Then at iteration t, you assign each point xj from x1, x2, xn to the nearest cluster center. And you do this by just solving this minimization problem. So xj is assigned to that mu-it cluster center that minimizes this Euclidean distance. And this assignment is denoted with CTJ. So CTJ is the cluster number of instance xj. And then you do a recentering. So after you found these class assignments, then for those points that belong to class I, so those xj instances that belong to class or cluster I, you calculate the mean, empirical mean of those points, and that will be your new updated cluster center. Any questions?
Graphically, how
Mm-hmm.
would you represent?
So I would just do this. So this is what the algorithm does. That you start from n instances, then you calculate so you start with you have n instances, you have say 3 guessed cluster center, and then for each point and each cluster center, you calculate these Euclidean distances. For each point, you choose the minimum distance. That will be the cluster center assigned to these points. So for example, this instance is assigned to this cluster, and then I calculate the empirical mean of these points. That will be the updated cluster center. Does it make sense? Okay, so then, so this is the algorithm. Yes?
Why start with randomized means and not a randomized partition?
Oh, you could do that too.
Okay.
Yeah. Either way is fine.
So when you do recentering, isn't that mu p plus 1 just the average?
Oh, yes, right, sure, yeah. So it's just for those points that belong to this cluster is just the empirical mean if you solve this minimization problem. So why I'm showing this way is just because you can see it's a two-step minimization problem. If I just show that, hey, here is the mean, it's not obvious that we do a two-step minimization problem. And in the next slide, we will see why it's interesting to see this algorithm as a two-step minimization process. Yes?
So you don't have to choose L2 norm there, do you?
No, you can choose anything you want.
But that might make it harder to find the cluster center.
Exactly. So depending on what kind of distance you use, if you choose L2, then it's the mean, empirical mean. For other distances, who knows what. But it's a good question. You could use your favorite distance.
Can we have different distance metrics in the two minimizations?
Yes, absolutely. And another thing, these guys here, they don't even need to be vectors necessarily. You can think of these as, say, functions, distributions. And if you have distributions, this could be like Kullback-Leibler divergence, whatever you want. You could still run these algorithms and see what happens. So you could cluster functions, you could cluster distributions. Okay? So if I present the k-means algorithm this way, then it's a two-step minimization problem. Here we have one minimization problem, here's another one. And let's try to see what this algorithm is really trying to minimize. So for that, we define a potential function f. So f potential function is a function of mu cluster centers, and so this is the k cluster centers, and C, which is just a cluster assignment which says that which point belongs to which cluster center. So C1 says that if, say, C1 is 2, it means that X1 belongs to cluster center cluster 2. So this is C1 Cn. And so this potential function f mu c is just the sum over all instances. So I use j. J is going from 1 to n. The cluster center mu that belongs to instance j, so that's mu cj minus xj squared. So that's my potential function. And I could rewrite this potential function this way. That is, I just group those instances that belong to class I, and then I sum from I1 to k, right? So this is a potential function. And what we can see is that actually what happens with the k-means algorithm, that you want to minimize this potential function f mu c in such a way that first step, you fix c, you minimize over mu. Then you fix mu, you optimize or you minimize over c. And then you repeat these two steps.
So, but literally that minimum you're optimizing over mu.
Right, and why?
Functions from n to k.
Sorry, once again?
So that minimum you're minimizing over mu, and c all the functions from n to k.
Right, so I fix mu, and I minimize over this c.
No, but
then
you're saying you're minimizing over mu and c.
Right. So that's my ultimate goal. So say I want to solve. Okay. So I define this potential function, and if I look at this potential function, I'm coming back to the k-means problem. You remember we defined the k-means problem. This. It's exactly that same potential function. So that's potential function is the k-means problem objective function.
Oh, so really you're just minimizing over functions from n to k.
What you mean minimize over functions?
What's the space in which you're minimizing that function?
I minimize
Over s.
So, for example, I can say I minimize over the allocations.
All partitions, which are functions from n to k. You're saying point.
Sure. In that way, yes. So I minimize over.
And then mu is just read off from whatever c is.
Yep.
In the late.
Right. But I can also just say that I want. So this is the k-means problem is equivalent to this, that I define the potential function this way. And I want to find the global optimum of the potential function in the space of mu, which are d-dimensional, k d-dimensional vectors, and c, which, if you want, they are functions. Right, so from n to the number of clusters.
What's then the... But you don't really do it, right?
So that's my ultimate goal. I cannot do that.
But you just do the...
So what I do, because this problem to solve this is NP hard. I cannot do that. So instead what we do, if I fix mu, the problem becomes easier. If I fix c, the problem becomes easier. So I just do this alternation, and I'm hoping that I will be lucky and will find a good local optimum point.
How do you express similarity in terms of the potential function? Meaning define the similarity you mentioned in your first slide.
Right, so that's actually defined here in the distance. So if you, so we just use Euclidean distance as a similarity. But if you are not happy with that, then you can just replace this to anything.
In your first slide, you mentioned you want to do two kind of optimizations. One is to maximize the similarity inside a group.
Right, so you can prove that actually this, so I'm not showing in the slides, but you can show that if you do that, that would happen.
Just the maximization and the minimization.
Yeah, right. Okay. But that's a good question. We are not going to prove that this potential function want to do something like that.
If you were, for example, convex in some sense, would this actually converge for sure?
So the issue is that f in mu and c, they are not. It's not convex.
So this is like a coordinate.
Right. So exactly. So what this is, it's a coordinate descent that you fix mu and you do a coordinate descent according to c. Then you fix c and you do a coordinate descent according to mu, and you converge somewhere. And you can prove that the algorithm will converge. You will stop somewhere. We just don't know the quality of that solution.
So we can show that the objective function itself is convergent, but how can show the sequence of the mu and the c itself is convergent? I mean, it's possible that I make a permutation of the class name labels and the objective function does not change, but the sequence of the partition and the mu may change. The proof does not show it's convergent, right?
Right, so what happens? So in each step, so we want to show that this two-step alternation,
I don't know how to show that the sequence of mu and the sequence of c is convergent.
So what's easy to show at least is that the optimization of f that will stop at some point, right? And indeed, and that's what we could do. The other thing you could do that you could say that with if you have randomly selected points, then you will not do this iteration with high probability. You cannot get stuck in these loops either because your points are in random locations. So that setting that you are saying, that's a very artificial setting, and that just will not happen for general points. But you are right that you have to be careful how to prove that. So let's just saying that for now what we prove is that this potential function, it will stop at some point after some steps. And why we cannot get into those loops with the allocations is just, let's just accept for now that for general points it will not happen. You have to have some very special points where.
So for the stop criterion of the optimization algorithm, it should be stated is the delta of the objective function itself, not the assignment of points.
So in practice, that will still work because you will never get into those C data sets where that would happen. So you can, in practice, you will be still safe.
Can you just enforce a clustering ordering and say always choose?
Yeah. So right. So another thing you could come up with some other like cluster ordering that could prevent that.
But I guess you have only finitely many possibilities, right?
Mm-hmm.
So you can visit each one at most one.
Right. So the issue is that how to handle the ties with this. But for general,
Even if you break them, for example, randomized, but if you visit one possibility, you will not visit it twice, I guess, but you only decrease it, so you know that
it might change the same. So if you decrease, you are good. But what happens if the distance, there's a point where the distance to a cluster center is...
you go back and forth between them? So what is the issue?
So it's
from one state to other state without
So you
changing.
keep track of the minimum anyway, so you hit the same minimum, you don't have any reason to move to the other point, as long as you know.
Yeah, you
So
start
itself, we can
yourself,
keep the same.
take to the end, right? So you're not gonna. Yeah.
But if you remember, I guess, if you have only finite many possibilities, it seems like you should actually just stop somewhere, right? Rather than going back and forth. Well, if there were only infinitely possibilities, probably you would just go into the loop, but now this time, because you have finite many points, you can have finite many assignments.
Right, so you have-
C's in a sense, right? Which generate finite many mu's.
That's true. So the one question is that for two assignments, you could have the same cost function number. That's what we need to check, that you cannot, and I'm pretty sure for general points settings you cannot have, but the question is that whether you could have two assignments where this guy is the same. And for general points, you will not see that. All right, so back to this point. So we want to minimize this potential function over mu and c. Gain potential function is defined this. And the k-means algorithm, just formally, you fix mu, you optimize over c. So you want to minimize over c1, c2, c, and this sum of square distances. And you can easily see that you can move this sum outside of this minimization and just minimize each term here over Cj because they don't depend on the other terms. So that's the first step of the k-means algorithm. And then when you fix C to optimize over mu, again, you can move this minimization inside this sum, and you just you need to minimize over mu I among those points xj that belongs to the cluster I. Okay, so this is just formally that with the k-means algorithm, you minimize this potential function such a way that you fix mu, you optimize over C, you fix C, you optimize over mu. Any questions? So we are all good for now, right? And as we discussed then, because of that k-means algorithm is a coordinate descent on F, you fix mu, you optimize over C, and we will see, so I'm just showing now, we will see why, that you can, this will be a special case of a so-called EM algorithm, where this will be the E, that is expectation step, and then we fix C, we optimize over mu, that will be the so-called maximization step, and we repeat this whole process. So this will be just a special case of a more general framework. Okay, so this is one algorithm how to do clustering. So if I ask you to implement this algorithm, it should be easy enough, right, to try it on data sets and see if you are happy or not happy with the results. This is one heuristic. And we are also going to discuss another heuristic, which is called Gaussian mixture model. That's also used for clustering. But again, any question about this? No. So we will look at the problem from a different angle, and this angle is, we will consider this problem as a density estimation, where we say we have again n points, and say just as a very first step, let's assume that I want to fit a Gaussian distribution over these points. So let's assume that, so this is x1, this is xn, and px theta is a Gaussian distribution with some parameter mu and sigma, and I want to find a theta that fits the best, theta that is mu and sigma, that fits best this set of points. Does it make sense? So we have a bunch of points. I want to fit a Gaussian, say a two-dimensional Gaussian in this case, to these sets of points. Okay, so in this case, we need to estimate this parameter theta. So here is the question. So what should we do if it turns out, so if I look at this data set, I might fit a Gaussian distribution where the density looks like this. But what should we do if I realize that, say my data set looks like this, so this is my new data set, and a single Gaussian just wouldn't fit this data set well? Then what can we do? So does it make sense? So you have this two-dimensional data set. I want to fit a Gaussian, but if I look at this data set, a single two-dimensional Gaussian just wouldn't fit nicely to this data set.
Cluster weight and then not two Gaussians.
Right, so then one thing we can do is that I make a partition somehow, and in each partition I would fit a Gaussian to these points and another Gaussian to these. That could be one approach. Right, so that's called partition algorithms, where you partition your domain, and depending on which part of the domain you are, you fit a different parametric model. Does it make sense? Okay, so that's one approach, and there will be another approach which is called mixture modeling, where you don't really do this partition. So this is a so with partition algorithm, again, what you do that you have the whole domain, you make a partition of that domain, and depending on where you are, so if I'm here, I fit a Gaussian to these points. If I'm here, I fit another Gaussian to these points. With mixture modeling, what we will do that with certain probability, each point will not just belong to one Gaussian, but it will be a mixture of many Gaussians, and that will generate the set of points. So we will see that formally, what I mean on that. Okay, so again with partition algorithms, so I just tried to illustrate that here, that I partition this two-dimensional domain to different parts, and in each part I fit a parametric model, say a Gaussian. And I want to say that this is like a hard assignment process in that sense that each, depending on which part you are, there's a fixed hard assignment that in this domain I will use this parametric model. Okay, with mixture modeling we will do a so-called soft assignment, and that's what I mean on that, that the density of a point at an arbitrary location, x, will be defined as a mixture of all these parametric models. So say I have k parametric models. Each has parameter theta I. So this is p x theta I. And with probability p theta I, with some prior probability theta I use model I. And to calculate the probability of given point x, I just use this mixture here. Does it make sense? So this is how this process works. That's why it's called generative model. I have capital K parameter vectors. So theta 1, theta 2, theta capital K. Each parameter will have a prior probability. That's denoted with pi I. So pi I is the probability of theta I. Pi I is the probability of parameter theta I. I randomly, according to these probabilities, I randomly select a parameter. And from that parameter, I randomly draw x. So for example, you can think of theta I as a mean and covariance vector of a mean and covariance matrix of a Gaussian distribution. With probability pi I select a parameter, and then if I selected a parameter, then using that Gaussian distribution, I draw a sample, and that will be my x. Yes?
So you're giving the vector pi, or we are also going to estimate pi?
We are going to estimate that. I'm just saying that if pi is given, then this is how would you generate more samples. What we are going to do, however, that pi is not given. I just have x1, x2, xn. And I want to estimate the parameters of the Gaussians, theta I, and I also want to estimate these pi I probabilities. Does it make sense? Okay, so that will be another, if we can do that, that will be another clustering algorithm in that sense that we will be able to calculate what's the probability that a point belongs to this, say, cluster I. Right, so we will be able to calculate the probability of y is I given x. And you can say that it's a self-assignment in that sense that for each I there will be a probability, but we can say that a point belongs to that cluster where this posterior probability is maximum. Okay, so say I already estimated these parameters theta I and pi I, then I can calculate this probability. What's the probability of a cluster center is I for a given point x? Sorry, what's the probability that for a given point x, this x belongs to cluster I? Right? So this is what happens here. Y is a cluster label. X given, so this is probability of x given theta I. It can be, say, a Gaussian distribution. So this is a Gaussian distribution with parameters mu I, sigma I, and all these parameters together are theta I. If I estimated the probability of theta i's, which I just denote with pi I, then after this, using Bayes rules, I can even calculate these quantities. That was the probability that the class label is I for a given point x. And
the probability of x given yi over the probability of yi, so pi I, right? That's what you're asking?
So I'm just saying that if I already estimated parameter theta I already estimated parameter pi I, then I will be able to estimate these probabilities, which and that's what's the solution of this clustering problem. That instead of giving a hard assignment that we did in k-means, we will give a soft assignment. We will say that this point x with this probability belongs to cluster I. Okay, so here I just demonstrate how you can draw samples again from a Gaussian mixture model if the parameters mu1, mu2, mu3 and the covariance matrices are known. Okay, so you choose a component I with probability pi I. So again, that's the probability that the class belongs, that this point belongs to class I. You choose this Gaussian distribution which has parameter mu I sigma I, and then you draw a data point x from this Gaussian distribution. So that's a generative process to draw points from a mixture of Gaussian distribution if you know the parameters mu I, sigma I, pi I. Okay, so this is formally the same thing. So, question? No, sorry. So the probability of a point x, given that it belongs to class I, will be a Gaussian distribution with minimum vector mu I and covariance sigma I. And then the overall probability of an observed data x will be just this, that it's a mixture of Gaussians. And we call that this is a mixture component. Again, this is Gaussian with parameter mean vector mu I, covariance matrix sigma I, and it has a mixture proportion which is just pi I. Okay. Okay, so our ultimate goal is that we have a bunch of observations, x1, x2, xn, and we want to estimate mu I, sigma I, pi I, and then calculate this probability. But to simplify our life, for now let's assume that, say, the covariance matrix sigma I is just a diagonal matrix with identical diagonal elements, so sigma squared times the identity matrix. So P, the probability of input point x, given that it belongs to cluster I, is a Gaussian distribution with some mu I, and again with this covariance matrix sigma I, which is just a diagonal matrix. And we assume now, just for now, that all the parameters are known. Okay? All the parameters are known. And then the question is, for a given x, we want to decide if it belongs to cluster I or cluster J. Then how should we do that? So all the parameters are known.
Just calculate the probability of, choose the highest.
Right, exactly. So we calculate these probabilities and we want to choose the highest one. So that's what we are going to do. But for now, let me just calculate the ratio of whether this point belongs to cluster I or cluster J. And if this ratio is bigger than 1, then I say that these points, say, beats cluster J. And so if I just need to choose between I and J, then I just need to calculate this ratio, right? If this ratio is bigger than 1, then points belongs to cluster I. If this point is less than 1, then it would belong to cluster J. And let's calculate the log ratio of this. Okay, it means that if this is bigger than 0, then this point belongs to cluster I. If it's less than 0, it belongs to cluster J. If I just need to make decision between I and J. Okay, and we can use Bayes' rule for that. So probability of y given x is the probability of x given y times the probability of y's. I do the same Bayes rule here. Probability of y given x is the probability of x given y times the probability of y. And just for fun now I divide both with px, px. That doesn't make difference for now. But now I can continue this, that right, so I just divided with px because of the Bayes rules, but they cancel out each other. Right, so let's see what we have. So probability of x given y is actually, it's a Gaussian distribution with parameter mu I, and because we assume that this covariance matrix has this nice structure, we have these sigmas here. Okay, so the log ratio of these two quantities just looks like this. If this is bigger than 0, then the point belongs to cluster I. If it's less than 0, it belongs to cluster J. So here is the question, how this decision boundary looks like. Right, so I'm in a, say, d-dimensional space. Parameters mu I, mu j, pi I, pi j, they are given. For a given x, I want to decide whether it belongs to cluster I, right? So say here is mu I, here is mu j. For a given x, I want to decide whether it belongs to this point or this point. And my question is does the decision boundary look like in this case?
It's a linear decision.
Right, it will be a straight line because you just have to solve this. When this is bigger than 0, you have to solve that for x. And if you see that because of this log, this cancel. Okay, so we need to do some calculations, but you can see this is quadratic in x after the log cancels the x function. So it's quadratic in x. This is quadratic in x as well, but because the covariance matrices are the same, those quadratic terms cancel out, and all that left is just linear terms and the constant. So this whole thing is linear in x. Okay, so I just did this calculation formally, but you can double check at home if I'm right. The point again, if you calculate these log likelihood ratios, then and you want to solve this when it's bigger than 0, then at the end it will be a constant times a linear constant plus a linear term w vector times x, where w is just a function of these parameters. So between any two cluster center ij, we will have a linear decision boundary. That's the point here. Okay, so if mu1, mu2, mu3 is given, then there will be a linear decision boundary between any of these 2 points. So here is another question. Yep.
If you allow sigma to be sigma I, right, then you get what do you get?
So here is a question. We got this linear decision boundary because we assume that the covariance matrices have this form. So what would happen if we don't do that? The covariance matrix can be anything general. Then how would these decision boundaries would look like? Right. So then what you would see is they would look like this. So say this is mu1, mu2, and mu3 somewhere here. So between any two clusters, it would be a quadratic decision boundary. But let me ask a simpler question for now. So we assume, again, covariance matrices have this form, sigma squared identity, and we decided that between any 2 points, there's a linear decision boundary, any 2 clusters. Why these guys cross each other in 1 point? So why this cannot happen? Or can this be happen? So we said that between any 2 points, mu1 and mu2, there's a linear decision boundary. Between mu2 and mu3, there's a linear decision boundary. Between mu1 and mu3, there's a linear decision boundary. Can this happen somehow that these linear decision boundaries just don't cross each other in a point? Yes?
Probability sum to 1, is that create another restriction that stops everything from getting bigger at once?
Can you go 1 slide back?
Sure.
So log pi or pi j. So you have 3 points, right? Pi 1, pi 2, pi 3. So the C.
Right. So if it helps, the pi 1 plus pi 2 plus pi 3 is 1. The sum of those. So this is what we do. We calculate. So we divide p, y, the probability of y belongs to cluster I given x. We divide this probability, again, the probability of y belongs to cluster J given X. This decision boundary apparently is linear, so between cluster I and cluster J there is this linear decision boundary. The question is whether this could happen or not.
I guess it cannot, because basically every boundary you're choosing between one of these points, and if the point lies in the middle, then basically you have a cyclic relation between these three.
Right. Yeah. So that's indeed what happens. That we have three numbers. You can always choose. So I want to decide whether this point belongs to cluster 1, cluster 2, or cluster 3. So I calculate this probability of belongs to cluster 1 given X, belongs to cluster 2 given X, belongs to cluster 3 given X. That's three numbers. Among these three numbers, there must be a maximum. Right? But if this was the case, so in this decision boundary, so this is my one decision boundary, it means that cluster 1 beats cluster 2 here. So cluster 1 beats here, cluster 2. If we are here, cluster 2 beats cluster 1. And if you think about this way, then if you are here, it would mean that cluster 1 beats cluster 2 beats cluster 3, cluster 3 beats cluster 1. So it would mean that among these three numbers, there is no maximum. So this cannot happen. Okay, so does it mean that the decision boundaries always be like this? So if I have 4 clusters, sorry, you might not be able to see. See, I have 4 clusters, not 3. For 3, we saw that the decision boundaries cross each other in one point. If I have 4, will it look like this always? Or if I have 5 clusters, will they look like this? Does my question make sense? So for 3 points, we saw that these decision boundaries go in one point. So now I can ask, what if I have 4 cluster centers, whether these decision boundaries between these 4 will always go through one point or not?
No, because all we're saying is that every region of space will have an associated maximum.
Right.
A cluster for which the probability is maximum. So that's not necessary. The diagram on the slide can be explained if there are 4 cluster centers.
Right. So indeed, if we have, say, 4 cluster centers, this one doesn't necessarily have to happen. It's just, you can think of again Voronoi diagrams that you can have regions that this point can have a cluster center mu1, mu2, mu3, and mu4 can be here now. So yeah. So any partition might be allowed that has straight lines in this case. Yes?
Since you let the pies be different, can't there be a case where there's one that's never the maximum? It never gets to be the maximum because...
So the pies can be different, but when you calculate this probability of y given x, then among these 3 numbers there will be a maximum.
I guess, is there a case where one label is never the maximum? Never gets to be the maximum. Basically, here we wouldn't have a decision rule of 3. There might only be 2 because one has such a low probability to begin with. Say I put 2 means right on top of each other, but gave one a pi that was bigger than the other, then we're never going to see.
Yeah, I can see your point. So the So what happens now that we have 3 clusters? So we always have mu1, mu2, mu3, right? So it means that somewhere in the space, say mu1 is here, mu2 is here, mu3 is here. And indeed, the pies can be very different. But what it means that we imagine that each mu, there's a Gaussian distribution that generates a sample from this Gaussian distribution, or there's a Gaussian distribution that generates sample from this distribution. There's a Gaussian distribution that generates sample from this distribution. And initially, so these pi's, they can be very different, but let's assume that none of them is 0. Okay? So it means that at least with some probability, there would be some small probability that, say, if pi 2 is the smallest, then this Gaussian distribution would generate a sample. And I think if you calculate the posterior distribution for a point here, then I think that that would be a winner.
But if a priori you have the points, then so if you said like at the beginning that you just have n points in RD.
Yep.
Then maybe all of them like really close to mu1, and then mu2 and mu3 get never used.
So how we start? So originally there's no endpoint. Originally there's a process that generates those endpoints.
So we didn't start with endpoints.
Right. So I assume that there's a process that generated those endpoints, and then I think there would be always, if you find the parameters perfectly, then I think you would use all those clusters. So your question is, if I want to fit 3 Gaussians, what if the optimum would be just 2 or something, right?
So still happen, it's just with probability, with almost surely not. Right? Because you can't just be so unlucky that all the points were in mu1. If you just randomly start generating points, you could be unlucky. But
yes. But you are right that, for example, if so these are the optimal points, and then someone throw points from here, then I would never use this guy.
I just mean that if you put the pi big enough on mu1, say, so that the ratio of your pi's AC, so make it so that the contour for mu1 is bigger at that part of mu2 than even mu2's is, you're going to cluster into mu1 just because you're pi dominated. So you're not going to get this nice 3 decision boundary even though you have 3 points.
But when we compare two Gaussians, if you move far enough, the tail of mu2 will always rise above the tail of
So that's
Yep.
tail behavior?
Yeah.
Okay, thanks.
There will be certain points which will cluster into mu2 even though mu1 might have
Just because it decays faster.
Yeah.
Right.
Yeah.
It doesn't depend on your data. Like if your data is really close together, you could imagine a big pi like making the other Gaussians totally irrelevant.
So I think it would never totally be irrelevant. All right. Okay, so this was just for the case where we assumed we know the parameters. But now let's start thinking of the question, what if we don't know these parameters? What if I don't know mu1, mu2, mu_k, I don't know sigma, the covariance matrix of the Gaussian, I don't know pi1, pi2, pi_k, then how can we estimate them? And so I put all these parameters to this parameter vector theta. And now our question in a maximum likelihood estimation, if we use maximum likelihood estimation, is find that parameter vector theta that maximize this the product of these probabilities. Okay, so probability of xj given the parameter vector theta is we already calculated this once here. So if I know all the parameters, then this is the probability of x given the parameters. It's just this expression. So this is pi I. This is a Gaussian distribution with parameter mu and sigma. So this is the probability of x given the parameters. That's this expression. So we know that. Because of that, we know this. Oops, sorry. We know this this term and we know this product. And what we need to do is right. So we know this quantity. This is so the probability of xj given theta. I just calculate it again. Is the product of so I marginalize out all these class labels, yj. So if I sum these probabilities from I to k, then it's these y's are they cancel out. And then I just use Bayes rules that probability of I and x is the probability of y and x is the probability of y times the probability of x given y. And the probability of y given theta, the probability of the class labels, that's pi I, that's our notation, and the probability of x given the cluster label and parameters, that's a Gaussian distribution with parameters in theta, that is mu I and sigma. Okay, so finally we know that if I want to find theta using maximum likelihood estimation, I just need to find that theta that maximizes this guy. Okay, so this is the likelihood function. And to simplify our life, we can take the logarithm of this to get rid of this product, and we will get the logarithm of this sum here. Okay, but after that, what to do? So we have this likelihood function or log likelihood function, and we want to maximize that in pi I, sigma, and mu I. How would you do that? So you have a cost function, objective function that you need to maximize in these parameters. And we have some other constraints as well, that, for example, the sum of pi i's should be 1, and they are non-negative. For now, it's sigma is just a real number, but it could be more generally a covariance matrix, and then another constraint that it has to be positive semi-definite matrix. All right, so we can have these other constraints. But again, here is this objective function, cost function. I want to maximize it. I need ideas how to do it. Yes?
Do the EM.
Right, so
okay, sorry. So
that's the point of doing this lecture. But if you don't know EM, and I assume many of you don't know EM, so if you don't know EM is not allowed, then what would you do?
Differentiate simply.
That's right, so it's a differentiable function, and then we know gradient descent. So we can calculate the gradient, and in case it's ascent. So, and then you can go towards the direction of the gradient to increase this function. So that's one way. But even better way would be to calculate the gradient, calculate the derivative, and solve when that derivative is 0, right? Because we want to find, say, a local optimum points. The issue is if you do that, you cannot solve that equation. Okay, so you can calculate the derivatives, but to solve when that equation is 0, it won't work. What you can do, though, is you can calculate the derivative and you can move towards the direction of the derivative.
Are you going to use Newton's or something?
Or you could do Newton methods as well. So you could calculate the second derivative as well and go ahead with that. Yeah. So you could do that. Your life will be not that easy just because the calculations are a bit ugly, and you have these other constraints that this pi has to be non-negative. They have to sum to 1. If you have a covariance matrix here, you need to pose another constraint that the matrix has to be positive semi-definite, and so on. So
you could do something like the cluster. You fix the pi's, then you optimize mu, then you re-update. So mu and sigma, and then
right. So okay. So that's a good point. So can we do that too? That we fix pi, optimize for mu I, and say let's fix 2, and so we fix pi I, fix sigma, optimize for mu I. Then I assume we would fix mu I, sigma, optimize for pi I, and so on. So we just do this 3 times. Right, so it would be like a coordinate descent kind of approach.
So in practice, what's the best way?
So this approach sometimes works, but sometimes you get in very bad local optimum points if you do that. So that's slightly better in is then just going for Newton methods. So at least, so calculating the Newton methods, it might look very ugly.
Can you not just sort of like start with Newton's, so you know you're approaching Deg level, and then sort of do that afterwards? So you sort of do the expensive stuff at the beginning, so you know you're approaching the neighborhood you should be, and then do some coordinate descent.
Right, so the issue with Newton method, again, that it's just, it's painful, right? Especially because you have other constraints, like, especially if that sigma is, say, a positive semi-definite matrix. And you have these other constraints that you have. So it's doable, it's a bit painful. And so intro class, so we want simple solutions. So a less painful other method, what you mentioned, that I fix those parameters and I optimize in the other. So I fix 2 of these 3, I optimize in the other. Quite often, the performance of those algorithms is very bad. So it just, you get stuck often in bad local optimum points. But at least the optimization problem is easier. But just the solution is not that useful. So we want to do something differently, and we will do EM for that. But time is over, so I will continue next lecture from there.
Just briefly, maybe you could comment on how is the EM going to be different from gradient descent?
EM, so it turns out EM will be a gradient descent as well. But with EM, you can calculate, so one problem with the gradient descent, you have to know the step size as well, right? And EM calculates a good step size for you, such that even if you move towards that gradient with that step size, all your constraints will be satisfied. That, for example, the pi's, they have to sum to 1 and they have to be non-negative. If you do EM, it will always be true.
Does that EM look more like